Hello, welcome to the video lecture series on digital image processing. Till the last class, we have seen various geometric transformations and we have seen how those geometric transformations can be used to model an image formation process. We have also seen that how to calibrate a camera given a particular imaging setup, and we have also seen that using two identical cameras, how we can have a stereo imaging setup using which the 3D coordinate of a point in the three-dimensional scene can be obtained. Now, in today's lecture, we will try to explain some interpolation operations. We will explain when the interpolation operation is needed, and at the end of today's lecture, the students will be able to write algorithms for different image transformations and the needed interpolation operations. Now, let us see that why and when do we need image interpolation and image resampling. So, let us first introduce this problem. Say for example, if we have a 3 by 3 image like this. So, we have this x y coordinate system, and this x y coordinate system we have a 3 by 3 image. So, I have an image pixel here, 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 here and here. So, you can easily identify that the coordinate of the image pixel, this particular image pixel is 0 0, this is 1 0, this is 2 0, this is 0 1, this is 1 1, this is 2 1, this is 0 3, this is 1 3 and this is 3 3. Now, let us try to apply some simple transformations, geometric transformations on these images. Say for example, I want to scale up this image by a factor of 3 in both the x dimension and y dimension. So, if I scale up this image by factor 3, in that case this 3 by 3 image will become a 9 by 9 image. And let us see how those image points, how the pixels in the 9 by 9 image can be obtained. So, I just apply a scaling operation by factor s x equal to 3 and s y is equal to 3. That is both in the x direction and y direction, I am applying a scaling of factor 3. So, naturally, this 3 by 3 image after being scaled up by factor 3 in both the directions will be converted to an image of 9 by 9. So, let us see how these pixel values will look like. Again I put this x y coordinate system. Now, you remember that this scaling operation is given by say x hat y hat is equal to s x 0 0 s y into column vector x y, where this S x 0 and 0 S y, this is the transformation matrix. X y is the coordinate of the pixel in the original image, and x hat y hat is the coordinate of the pixels in the transformed image. So, if I simply apply this scaling transformation, then obviously this 0 0 point will lie at location 0 0 in the transformed image. But what will happen to the other image points? So, because this will be converted to a 9 by 9 image, so let us first form a 9 by 9 grid. Okay. So, now you find that this 0 0 pixel even after this scaling transformation remains at location 0 0. But the other pixels, say for example, this pixel 1 0, which was originally at location x coordinate equal to 1 and y coordinate equal to 0, that will be transformed to y coordinate will remain as 0, but now x coordinate will become equal to 3. So, this point will be mapped to this particular location. Similarly, 2 0 will be mapped to 6 0 location. So, this becomes 1, 2, 3, 4, 5, 6. So, this pixel will be mapped to this particular location. Similarly, 0 1 pixel will now be mapped to 0 3 location, 0 2 pixel will now be mapped to 0 6 location. So, 3, 4, 5, 6. Similarly, I will have pixels in these different locations in the scaled image. But you find that because in the original image I had 9 different pixels, even in the transformed image I got 9 different pixels, that is 3 pixels in the horizontal direction and 3 pixels in the vertical direction. But because I am applying a scaling of factor 3 in both x direction and y direction, my final image size after scaling should be 9 pixels in the horizontal direction and 9 pixels in the vertical direction. So, you find that there are many pixels which are not filled up in this scaled up image. So, those pixels, some of them I can simply mark. So, this is one pixel which is not been filled up, this pixel has not been filled up, this pixel has not been filled up, this pixel has not been filled up, this one has not been filled up. So, likewise there are many pixels in this particular image, in this scaled up image which has not been filled up. Let us try to take another example. So, I apply a instead of scaling, I apply a rotation operation to all these different pixels. So, I have this 3 by 3 pixel, and suppose I rotate this image by an angle of 45 degree in the clockwise direction. So, if I rotate this image by 45 degree in the clockwise direction, you know that we had a transformation matrix which takes care of rotation, and that is given by cosine theta, sin theta, then minus sin theta, cosine theta. So, this is the rotation matrix which when applied to different pixels in the original image will give you the pixels in the rotated image. So, in the rotated image I can represent these pixels by x hat, y hat, whereas my original pixels are x and y. And in this particular case, the value of theta is simply 45 degree. So, if I apply this transformation, the rotation transformation to all the pixels in the original image, you find that 0 0 location will be transformed to location 0 0 even in the transformed image. 0 1 location will be transformed to 0.707 and 0.707 location. Then 0 2 point will be transformed to location 1.414 and 1.414. Similarly, 1 0 location, pixel at location 1 0 will be transformed to location 0.707 and minus 0.707. Location 1 1 will be transformed to location 1.414 and 0, and location 1 2 will be transformed to location 2.121 and 0.707. Similarly, the other coordinates 2 0, this pixel will be transformed to location 1.414 and minus 1.414. 2 1, this will be transformed to location 2.121 and minus 0.707, and 2 2, this particular image pixel will be transformed to location 2.828 and 0. So, these are the various transformed locations of the pixels in the rotated image. Now, if you just look at these transformed locations, you find that the coordinates that we get are not always integer coordinates. In many cases, in fact, in this particular example, in most of the cases, the coordinates are real valued coordinates. But whenever we are going to have a digital image, whether it is the original image or the transformed image, even in the transformed image, all the row index and the column index should have an integer value. I cannot represent any real number or a fractional number as a row index or a column index. So, in this case, whenever I am going for this particular transformation, what I have to do is, whenever I am getting a real number as a row index or a column index, I have to take its nearest integer where that particular pixel will be put. So, in this case, for the original image location 0 1, which has now been transformed to location 0.707 and 0.707, this has to be mapped to a pixel location 1 1 in the transformed image. So, if I do that mapping, if you find that all the pixel locations will now be mapped like this. So, I put a new grid, and the new grid will appear like this. So, you find that the 0 0 location has been mapped to 0 0 location. So, I have a point over here, pixel over here. 0 1 location in the original image has been transformed to 0.707 and 0.707 in the transformed image. So, what I have to do is, I have to take the nearest integer of these fractional numbers where this particular pixel will be put. So, 0.707 in the x direction and 0.707 in the y direction will be mapped to 1 1 in the transformed image. So, this 0 1 point will now be mapped to location 1 1 in the transformed image. So, I get a point here. Similarly, 0 2, you find that the corresponding transformed location is 1.414 and 1.414. Again, the nearest integer of 1.414 is 1. So, this point 0 2 will also be mapped to location 1 1 in the transformed image. 1 0 in the same way will be mapped to location 1 minus 1. So, 1 0 will be mapped to this particular point in the transformed image. 1 1 will be mapped to 1.4140. Here again by integer approximation, this point will be mapped to 1 0 location in the transformed image. So, I have a pixel in this particular location. 2 1 point will be mapped to 2.121 and 0.707. So, again by integer approximation, I map this pixel to 2 1. So, this is the point where the pixel 2 1 1 2 of the original image will be mapped. In the same manner, 2 0 point will be mapped to location 1 minus 1, where I already have a particular point. 2 1 location will be mapped to location 2 minus 1. So, I will have a point here. 2 2 location will be mapped to 3 0 in the transformed image. So, I will have a pixel in this particular location. So, you find that in the original image we had 9 pixels, whereas in this rotated image we are going to have only 7 pixels. And this comes because when you are rotating any image, the integer coordinates in the original pixel, some of them turns out to be fractions or real numbers in the transformed image, and these fractions or real numbers cannot be represented in digital form. So, we have to round those numbers to the nearest integer, and which leads to this kind of problem. And not only this, you find that if I just rotate this original image, ideally my rotated image should have been something like this. Okay. But here you find that there are a number of points where I do not have any information. Say for example, this point I do not have any information, this point I do not have any information, this point I do not have any information. Similarly, all these points I do not have any information, and the reason is because of digitization. So, to fill up these points, what I have to do is I have to identify in the transformed image what are the locations where I do not have any information. So, to take the simple case, take the previous one. Here you find that I do not have any information at location 1 1 of the transformed image or the scaled image. So, because I do not have any information here, now I have to look in the original image to find out which value should be put at this particular location. Now, because this image I have obtained using a scaling of 3 in both x and y direction, if I want to go back to the original image, then to this transformed image I have to apply a scaling of 1/3 in both x direction and y direction. Now, find that in the transformed image, this particular location, this particular pixel has a coordinate of 1 1. So, if I transform this, inverse transform this using the scaling factor of 1/3 and 1/3, I get in the original image the x coordinate should be equal to 1 upon 3, the y coordinate should also be equal to 1 upon 3. Now, here comes the problem. In the original image, I have the informations at location 0 0, I have the information at location 0 1, I have information at location 1 0, I have information at location 1 1, but at location 1 3 and 1 3 I do not have any information, because you remember from our earlier classes that whenever we have gone for image digitization, the first step we had done was sampling, and the second step that we had done was quantization. Now, the moment we sampled the image, what we have done is we have taken some representative value from discrete grid points. We have not considered the intensity values at all possible points in the continuous image. So, in the process of sampling, whatever value was there at location 1 upon 3, 1 upon 3 in the continuous image, that information is lost. So, in the digital image, at this particular location 1 upon 3, 1 upon 3, I do not have any information. So, what is the way out? Now, the only process that I have to do is I have to go for approximation of the intensity value which should have been at this location 1 by 3 1 by 3. Now, how to get that approximate value? That is the problem. So, only way in which this can be done is I have to interpolate the image in these points where I do not have any information. And after interpolation, so in these locations where I do not have any information in my discrete image, I have to interpolate the values in these locations, and after interpolation I have to check what should be the interpolated value at location 1 by 3 1 by 3. And whatever value I get at this location 1 by 3 1 by 3, this particular value has to be taken to fill up this location 1 1 in the transformed image. Similar is the case for the other transformation, that is rotation. In this case also, this rotated image we have obtained by rotating the original image by 45 degree in the clockwise direction. So, whenever I find any point in the rotated image where there is no information, what I have to do is that particular coordinate I have to inverse transform, that is I have to give a rotation to that particular point by minus 45 degree, go back to the original image point, and obviously in this case in the original image these row column indices will not be integers, but they will be real numbers or fractions. And because we have real numbers or fractions for which we do not have any information in the original digitized image, we have to go for interpolation, and after interpolation we have to go for resampling to find out what should be the intensity value or approximate intensity value at that particular location. Then take that intensity value and put it into the point in the transformed image where I do not have the information. So, this is why you find that the interpolation and resampling is very, very important whenever you are working in the digital domain or you are doing some sort of transformations or over a digital image. Now, whenever we go for interpolation, so this gives the situation that we have a one dimensional signal f t of function t, and after sampling we have got the sampled signals f s t. So, here you find that after sampling what we have got is the sample values which are represented by f s t. Now, as we have f s t, these values are present only at discrete locations. So, at any intermediate location in this particular one, we do not have any information of this function f t, and because we do not have these informations, we have to go for interpolation for all those values of t where we do not have the samples present. And after interpolation, again we have to go for resampling to fill up those positions. So, this slide shows a sampled one dimensional signal f t of a function t. So, after sampling we have represented the signal by f s t, where f s t is nothing but a sequence of sample values. So, in this case you find that we have the values available for say t equal to 0, here I can put t equal to 0, at t equal to 1, t equal to 3, 2, t equal to 3 and so on. But I do not have any information for a value of t which is in between 0 and 1. So, if I need to obtain a value of f at location say 0.1 0.3. Then what I have to do is, I have to interpolate this function f s t, and I have to find out after resampling that what will be the value of the function at t equal to 0.3. So, this is why the interpolation and resampling is very, very important whenever you are working with a digital signal and digital image in particular, and you are going for any type of transformation, particularly the rotation and translation of the digital image. Usually, the translation operation, when if it is only translation, does not need any kind of resampling or interpolation. Now, whenever we interpolate an image, the interpolation operation should have certain desirable properties. Firstly, the interpolation function that you use for interpolating the discrete values, that should have a finite region of support. That means, interpolation should be done based on the local information, it should not be based on the global information, or it should not take into consideration all the sample values of that particular digitized signal. The second desirable property is the interpolation should be very smooth. That is, the interpolation should not introduce any discontinuity in the signal. And the third operation is the interpolation should be shift invariant. So, if the signal is shifted or given some translation, then also the same interpolation function should be available, should be done. And the B-spline function is one such function which satisfies all these three desired properties. Now, let us see what is this B-spline function. B-spline function is a piecewise polynomial function that can be used to provide local approximation of curves using very small number of parameters. And because it is useful for local approximation of curves, so it can be very, very useful for smoothing operation of some discrete curves. It is also very, very useful for interpolation of a function from discrete number of samples. So, let us see what is this B-spline function. A B-spline function is usually represented by, say, x t is equal to sum of p I into b I k t, where you take the summation from I equal to 0 to n, where 0 to n, that is n plus 1 is the number of samples which are to be approximated. Now, these points p I, they are called the control points, and b I k is the normalized B-spline of order k. So, b I k, this is the normalized B-spline of order k, and p I are known as the control points. So, these control points actually decide that how the B-spline functions should be guided to give you a smooth curve. Now, this normalized B-spline, that is b I k, can be recursively defined as b I 1 is equal to 1 whenever t I is less than or equal to t less than 1. So, this is b I 1 of t, it is equal to 1 whenever T I is less than or equal to T and which is less than 1 and B I 1 T is equal to 0, whenever value of T takes other values. So, this is equal to 1 for all values of T lying between T I and 1, T I is inclusive and B I 1 T is equal to 0 for any other value of T. And then we can find out B I of and K of T using the relation. So, B I K T is equal to T minus T I into B I K minus 1 T upon T I plus K minus 1 minus T I plus T I plus K minus 1 into B I plus 1 K minus 1 T upon T I plus K minus T I plus 1. So, once we have B I 1 for different values of T, then from this B I 1 we can recursively compute the values of B I K using this relation. Now, find that once we have this relation of B I K T, you can easily verify that once I have B 0 K T, then B I K T is nothing but translates of B 0 K T. So, this B I K T can be written as this is nothing but B 0 K T minus I. So, this can be easily verified from the way this B-spline function is defined. Now, this B-spline function for various values of I and k can be obtained like this. You can easily get that B 0 1 t will be equal to 1 whenever 0 less than or equal to t less than 1, because earlier we have said that B I 1 t is equal to 1 whenever t I is less than or equal to t, which is less than 1 and it is 0 otherwise. So, just by extending this, I can just write that B 0 1 t will be equal to 1 whenever t lies between 0 and 1, 0 inclusive, and it will be equal to 0 otherwise. So, you find that B 0 1 t is constant in the region 0 to 1. Similarly, we can find out B 0 2 t will be equal to t for 0 less than or equal to t less than 1. It will be equal to 2 minus t for 1 less than or equal to t less than 2, and it will be equal to 0 otherwise. Similarly, you can find that B 0 3 t can be written as t square by 2 for 0 less than or equal to t less than 1. This will be equal to minus t square plus 3 t minus 1.5 for 1 less than or equal to t less than 2. It will be 3 minus t square upon 2 for 2 less than or equal to t less than 3, and it will be 0 otherwise. Similarly, we can also find out B 0 4 t will be equal to t cube by 6 for 0 less than or equal to t less than 1. It will be equal to minus 3 t cube plus 12 t square minus 12 t plus 4 by 6 for 1 less than or equal to t less than 2. It will be equal to 3 t cube minus 24 t square plus 60 t minus 44 divided by 6 for 2 less than or equal to t less than 3. This will be equal to 4 minus t cube by 6 for 3 less than or equal to t less than 4, and it will be 0 otherwise. So, we can obtain all these values from the definition of the definition of the B-spline function that we have defined earlier. Now, whenever I write this B I k, this k is called the order of the Bezier order of the B-spline function. Now, after giving these equations, let us try to see that what is the nature of these Bezier of these B-spline functions. So, you find that B I 1 t, because it will be equal to 1 for I equal to 1 to 2, between I equal to 1 to 2, this B I 1 t will be equal to constant and it will be equal to 1. So, this first figure in this particular case tells you that what is the nature of this B I 1. The second figure shows what is the nature of this B-spline function if it is B I 2 t, and it shows that it is a linear function. So, B I 2 t will lie between, will have a support from I to I plus 2, and the points which will be supported by this B I 2 t are I plus 1 and I plus 2. Similarly, a quadratic function which is B I 3 t is given by this figure, and a cubic function which is B I 4 t is given by this fourth figure. And here you find that the region of support for this cubic function is 5 points, the region of support for quadratic function is 4 points, the region of support for the linear B-spline is 3 points, whereas the region of support for for the B-spline of order 1 is only 2 points. So, in all the cases the region of support is finite. Now, let us see that using these B-splines how we can go for interpolation. As we have said earlier that using these B-splines, a function is approximated as f t equal to p I b I 1 t or b I k t, where I varies from 0 to n. So, in this case, let us take the value of k to be equal to 1. That means, we have a B-spline of order 1, and we have shown that if we have a B-spline of order 1, then the nature of the B-spline function is it is constant between I and I plus 1, and which is equal to 1. So, using this, if I try to interpolate this particular function as shown in this diagram, which are nothing but some sample values, I take say t equal to 0 here, t equal to 1 here, t equal to 2 here, 3 here, 4 here, 5, 6, 7, 8 and so on. Now, if I want to find out say f of 1.3. So, f of 1.3 should lie somewhere here. So, to find out this f of 1.3, what I have to do is, I have to evaluate this function f t, where I have to put t is equal to 1.3, and this f t is given by this expression, that is p I b I 1 t, where I varies from 0 to n. Now, find that this b I t, when if I take I equal to 1, so b 1 1 is a function like this. So, in between 1 and 2, this b 1 1 is constant, and that is equal to 1. Okay. So, if I find out the value at this particular point, it will be p I, that is f s 1 multiplied by b 1 1 at t equal to 1.3, and which is equal to 1. And this b 1 1 is equal to 1 for all values of t from t equal to 1 to t equal to 2, but excluding t equal to 2. So, if I interpolate this function using this b I 1 t, you will find that this interpolation will be of this form. Sorry. This interpolation will now be of this form. So, it goes like this. So, all the values at all points between t equal to 1 and t equal to 2, the interpolated value is equal to f s 1. Similarly, between t equal to 2 and t equal to 3, the interpolated values is equal to f s 2, and so on. Similarly, if I go for interpolation using, say, linear interpolation, where value of k is equal to 2, in that case again you find that if I put, say, t equal to 0 here, t equal to 1, t equal to 2, t equal to 3, 4, 5, 6, 7, 8, like this. Now, b 1 2 is a linear function between 1 and 3. So, b 1 2 is something like this. Similarly, b 2 2 is something like this, b 3 2 is something like this. So, if now I want to interpolate, or I want to find out the value of this function at point, say, 2.5, at t equal to 2.5, say here, then you find that the sample values which take part in this interpolation are f 2 and f 3, and by using these two sample values by linear interpolation, I have to find out what is the interpolated value at t equal to 2.5. Now, you take a case that I want to interpolate this function value f t at t equal to, say, 3.1, that means somewhere here. So, if I want to do this, then what I have to do is, this will be an interpolation of p 3. So, this will be nothing but p 3 into b 3 2 at point t equal to 3.1 plus, you can easily find out, it will be p 4 into b 4 2 again at point 3.1. So, I want to interpolate this value here. Now, find that weight of this p 3 is given by only this much, whereas weight of this will be p 2 b 2 2 and p 3 b 3 2. So, weight of b 2 is given by this value, whereas weight of p 3 is given by this value. So, when I am interpolating at 3.1, I am giving less weightage to P3, which is nearer to this particular point t equal to 3.1, and I am giving more weightage to this particular point P2, which is away from 3.1, which is not very logical. So, in this case, we have to go for some modification of this interpolation function. So, what is the modification that we can think of? The kind of modification that we can do in this case is, instead of having the interpolation as say f t is equal to p I b I k t summation over I equal to 0 to n, I will just modify this expression as f t is equal to, I will put same b I p I, but b I will shift by some value. So, I will take it b I minus s k t, again I will vary from 0 to n, and the value of this I will be value of this shift s will depend upon what is the value of k. So, I will take s is equal to 0.5 if I have k equal to 1, that is constant interpolation. I will take s equal to 1 if I have k equal to 2, that is linear interpolation, and I will take s equal to 2 if k is equal to 4, that is I have cubic interpolation. Now, you find that I have not considered k equal to 3, which is the quadratic interpolation, because quadratic interpolation leads to asymmetry in interpolation. If I go for other interpolations like k equal to 1 with of course, a shift of b I k by a value of 0.5, so s equal to 0.5, or if I take k equal to 2 with s equal to 1, or if I take k equal to 4 with s equal to 2, what I get is asymmetric interpolation. So, these are the different interpolation, the B-spline interpolation functions that we can use for interpolating the function from sample values. So, this shows the situation when we have shifted this b I 1 by a value 0.5. So, here you find now that b I 1 is constant from minus 0.5 to plus 0.5. Similarly, 0.5 to 1.5, it will be from 1.5 to 2.5 and so on. Similarly, b I 2, now it is the regions of support for b 0 2 is between minus 1 and 1, for b 1 2 is from 0 to 2 and so on. So, by using this, similarly for cubic interpolation, I do the corresponding shifting, and by using this, now the interpolation can be obtained by as, if I go for cubic interpolation, that f t is equal to p I b I minus 2 4 t, where the summation has to be taken from I equal to 0 to I equal to n. And here it gives that if I want to interpolate this function at this particular point, the weight given by this particular function sample is only this much, the weight given by this particular sample is this much, the weight given by this particular sample is this much, the weight given by this particular sample, this sample is weighted by this much. So, by taking this weighted average, the weights given by these B-spline functions, I can find out what will be the interpolated value at this particular location. So, if I use that cubic interpolation function, possibly I will have for this set of sample values an interpolation, a smooth interpolation like this. So, maybe this kind of smooth interpolation is possible using the cubic B-spline function. Now, let us see some of the results on the images that we have obtained. So, this is the example of a scaling operation. I have a small image which is scaled up by a factor 3 in both x direction and y direction. You find that the image on the left side is obtained by scaling without applying any interpolation. So, obviously, you find that here the image appears to be a set of dots where many of the pixels in the image are not filled up. If I go for nearest neighbor interpolation or constant interpolation, this is the reconstructed image that I can get, and you find that here I have the blocking artifacts. I mean, the image appears to be a collection of blocks. Similarly, if I go for other interpolation techniques, if I use quadratic B-spline interpolation, then this is the quality of the image that we obtain. If we go for cubic B-spline interpolation, then this is the quality of the image that we can obtain. The same result is also the same experiment is also done in case of rotation. This particular image has been rotated by 30 degrees, and if I do not apply any interpolation. So, without interpolation, the rotated image is shown on the left hand side, and here again you find that there are a number of black spots in this rotated image which cannot be filled up, which could not be filled up because no interpolation was used in this case. Whereas in the right hand side, this particular image after rotation has been interpolated using bicubic interpolation function. So, you find that all those black spots in the digital image have been filled up. Now, let us see the answers of the quiz questions that we had given in the last class. In the last class, we had given a quiz question for finding out the 3D coordinate point of a world point, where its coordinate in the left camera and the coordinates in the right camera are given. The value of the focal length lambda was given as 40 millimeter, and the x coordinate in one case was given as 0.2 in the left camera, and in the right camera it was given as 0.4, and the camera separation was given as 6 centimeter, that is 60 millimeter. So, if I simply use the formula, say z equal to lambda plus lambda b by x 2 minus x 1, you find that this will be equal to 40 plus 40 into 60 divided by 0.2, because x 2 minus x 1 in this case is 0.2, and which comes out to be 12040 so much millimeter. Okay. So, this is the value of z, that is the depth information, and once I have the value of z, then the 3D coordinates x and y can be computed from this value of z. So, x is nothing but x naught by lambda into lambda minus z, which is nothing but 0.2 upon 40 into minus 12000, which is equal to minus 60 millimeter, and by applying the same procedure, you can find out y equal to minus 90 millimeter. So, this is about the first question. Second question was to find out what is the minimum depth that can be obtained by using the stereo camera, where the geometry of the stereo camera was specified. Now, this is also very simple. What you can do is, you find that we have two cameras with certain dimension of the imaging plate. They have been specified certain focal length, and if I just find out what is the limit of the image points. So, you find that if there is any point beyond this particular line, this point cannot be imaged by the left camera. If there is any point in this direction, that cannot be imaged by the right camera, because it goes beyond the imaging plate. And also, for finding out the depth information, it is necessary that the same point should be imaged by both the cameras. So, the points which can be imaged by both the cameras are only the points lying in this particular conical region. The points belonging to this region or the points belonging to this region cannot be imaged by both the cameras. So, all the points must be lying within this. So, the minimum depth which can be computed is this particular depth. Now, I know what is the separation between the cameras, I know what is the dimension of the imaging planes. Okay. I also know what is the focal length. So, from these informations, by using the concept of similar triangles, you can easily find out what is the minimum depth that can be computed by using this stereo setup. Now, coming to today's questions. So, the question number 1, if an image represented by the following matrix is scaled up by a factor of 3 in both x and y directions, what will be the scaled image with nearest neighbor interpolation and bilinear B-spline interpolation? The second question, if the same image, which is given by this matrix again, is rotated by an angle of 45 degrees in the clockwise direction, what will be the rotated image? Use bilinear B-spline for interpolation. Thank you.